Good morning, and welcome to Evoqua's webinar on IonPure Continuous Electrodeionization Technology. My name is Sonia Muniz, and I am the Americas Sales Manager for the IonPure technology under our APT segment here at Evoqua. Today, I'm joined by a group of fantastic colleagues that together will be bringing this webinar to you. Conducting our webinar today is Mr. Michael Cavalieri. Mike is our North America Sales Manager. He has been in the water industry for over 16 years and has been our sales lead for North America for over 4 years. We're also joined by Mr. John Wood. John is IonPure's Applications and Technical Support Global Lead. He was part of the team that commercialized EDI back in the 80s and has over 35 years of experience in EDI. Before we proceed with our webinar today, I will go over a couple of house items. If you're having audiovisual problems with our presentation today, please ensure that you have selected the computer audio when logging in. Check the GoToWebinar audio visual settings. Test your sound. Reboot the webinar platform and computer if necessary. And as a last resort, you can always dial in utilizing the number supplied in our email invite. We will be taking live questions as we proceed today with our webinar presentation. If you have any questions, please make sure you type those in the questions box located in the GoToMeeting dashboard. We will also hold a live Q&A towards the end of our webinar today, in which our team will together answer any questions you might have about our fantastic technology. Now, without further ado, here's Mr. Michael Cavalieri.
Thank you, Sonia, and hello, everyone. This is Michael Cavalieri. I am the sales manager with IonPure. I work out of the R&D facility in Lowell, Mass. So I want to thank you very much for joining us today. First thing I wanted to go through was the agenda. This is a 30-minute webinar, and it will be followed by a 30-minute question and answer session. I'm going to do my best to keep it right to 30 minutes. So to go through the agenda with you, the first thing is I'll go through a little bit about Evoqua and then tell you about the product history of IonPure. I'd like to go into the basics of CEDI, the technology, and then we'll talk a little bit about the markets and the applications for CEDI, or continuous electrodeionization, but specifically focus on the power generation market. I'll then provide an overview of the IonPure products that we offer, and then do a comparison of mixed bed DI versus CEDI. I'll present our warranty, some additional services that we offer, and provide you how to obtain various resources that we offer primarily through the web. And then we'll go into the question and answer session. So a little bit about Evoqua and IonPure. Evoqua is a publicly traded company on the New York Stock Exchange under the call letters AQUA. We went public about 3 years ago, and it's been a really fun ride and very successful. IonPure is a product of Evoqua that was developed some years ago. All the manufacturing of the modules are done in Tewksbury, Mass. Here at the R&D facility, we've got a number of engineers, and through the organization, we have a number of people that are here to support the OEMs and system integrators for IonPure. We've got a dedicated engineering staff. Many of the folks here have been here for more than 30 years. They've got a tremendous amount of know-how, fully understand how to apply CEDI, and we feel we've got one of the most complete products in the industry on the market. So first, a little history of EDI. You can see here that it has its origins back in the late 1890s when membranes were used to treat electrolytes. And there were advancements over the years up until, say, 1993. And then you see the first boiler feed application at a power plant in Huntington Beach. Further advancements, if you go to 2004, and you'll see we introduced our first stackable 50-gallon-a-minute leak-proof EDI module under Veolia at the time, which is now Evoqua. A little bit on the evolution of deionization. You can break it down into 3 generations. In the first generation, you've got the flow of water through pretreatment and then into cation and anion exchange, and then into mixed bed resin and chemical regeneration. Later, in the second generation, there was the introduction of reverse osmosis, and you still had mixed bed and chemical regeneration, bringing us to the current generation where you have pretreatment, RO, and then into CEDI with no chemical regeneration. So wanted to give you a little bit of a view of the evolution of the technology in terms of the flow rate and the footprint. So if you look at this slide on the left, you'll notice there was a system back in the 80s that had 20 gallons a minute of flow, and it occupied 20 square feet. So going to the right, you'll notice that 20 gallons a minute jumps to 60, 120, and then up to today's standards, which are 528 gallons a minute in just 31 square feet. So a tremendous improvement. I'd like to go into the basics of CEDI technology. First, this is an electrochemical process, and it's based on the science of opposite charges attract and like charges repel. Essentially, you've got cations migrating towards the cathode and anions migrating towards the anode. And you add ion exchange membranes and you get electrodialysis. This membrane is a sheet form of the ion exchange resins, and what's happening is you essentially can take the resins and grind them up and recast them into a sheet form. The membrane has a fixed charge and it's selectively permeable. You've got an anion membrane with a positive charge, it's anion permeable, and it repels cations like sodium. The cation membrane has a negative charge, it's cation permeable, and it repels anions like chloride. These membranes are impermeable to water. This is a little counterintuitive if you're not familiar with the technology. Most people think that the water is going through the membranes, but the water is actually flowing past but not through the membranes. These ions are diffusing through the water that's trapped in the membrane, and you've got alternating membranes using screen and gasket channels. Essentially, the salts are transferring out of the product stream and into the reject stream. Electrodialysis as a technology is used for desalting brackish water. It's not effective at very low TDS because it does not remove weakly ionized or neutral species like silica, boron, and carbon dioxide. So you add in resin from electrodialysis and you create continuous electrodeionization. And this resin is a technology improvement on electrodialysis. The difference between the two is that CEDI uses ion exchange resin between the membranes, and that's not the case with electrodialysis. This resin is very conductive. It facilitates water splitting, which is really important to allow the resin to regenerate. The resin needs a special cell design to contain it. The reason for that is this, if you've ever felt the resin, it's very slippery, small beads. You put it in water, it's essentially fluidized. So you really need a special design to contain all that. CEDI is often referred to as filled cell electrodialysis. When the salt is removed with electrodialysis, this system can no longer transport current and remove ions. So you have no current, then you have no water splitting and no regeneration. CEDI, on the other hand, is referred to as, or CEDI is designed, to produce high purity water. The ion exchange resin allows for the removal of weakly ionizable species such as silica, boron, and carbon dioxide. This slide demonstrates ion removal and water splitting. Cations like sodium and hydrogen pass through the cation membrane, whereas the anions like hydroxide and chloride pass through the anion membrane. Water is coming in through the top, and then the product and the reject are flowing through the bottom. You put it all together and you see here our VNX module. This is our flagship product for the power industry. It has some of the highest flow rates of any module on the market. Down below you see the LX module here, and this is also used in the power industry. It has been used for many years, and with the introduction of the VNX, we just are seeing most applications, because of the high flow rates, are using our VNX module. I'd like to talk a little bit about the markets. The main markets for CEDI technology are the power industry, semiconductor, and pharmaceutical. But today we're going to focus on the power industry and how CEDI delivers superior performance compared to mixed bed DI. This chart here, it demonstrates how, as the cost per gallon per minute per module goes down, the market acceptance of CEDI, shown by the solid line here, goes up, okay, continues to grow. Early CEDI modules back in the mid-'80s produced only 10 gallons a minute back here, as compared to today's VNX Max modules, which flow at 66 gallons per minute per module. So the greater the flow rate, the lower the overall cost, capital cost, and the greater adoption rate of mixed bed over mixed bed DI. CEDI is an ideal technology for the power market. The main issue for power generation is the impact of scale formation on the turbine blades, which reduce efficiency. And with the size of some of these markets, you can have just a slight reduction in the efficiency of the power generator, and it can cost some very large dollars. So it's very important. As you can see from this slide, high quality water is needed for boiler makeup in the range of 0.1 microsiemens conductivity or better. In some power applications, we recommend you have a 2-pass RO for the CEDI feed water, and to also very carefully control the CO2 in the system. So why is the power industry choosing CEDI over mixed bed deionization? Well, for the firstly, no chemicals are needed for regeneration with CEDI. This is a huge advantage. Another is that there's less downtime, that this is a proven technology. CEDI has been around for dozens of years, and it's absolutely a proven technology in power plants. You'll experience very consistent performance with CEDI technology. Our modules are guaranteed to be leak-free. This type of a system has superior safety over mixed bed DI. You're not trucking in chemicals and regenerating on site. There's less space required. It's also lower cost to operate one of these systems. You've got reduced labor. Our process, CEDI, is a continuous process. It's not a batch process. Mixed bed DI is a batch process. Overall, you've got a reduction in the environmental health and safety risks when you're using CEDI. The above chart here on the left highlights how mixed bed technology is a batch process. So when the resin begins to deplete, the water quality goes down, and the system cycles through the chemical process again and again, regenerating the resin. Compare this to CEDI technology, or the chart on the right, and you see a consistent line here. It shows this consistent water quality. So this is one of the main differences with CEDI technology. I'd like to give you an overview of our products. This chart here shows you that we offer many products from the LabXT through the VNX, and this is showing their flow rates. So looking at the LabXT, this flows at fractions of a gallon per minute compared to the MX module, which is up to 2 to 3 gallons a minute. The LX, our largest module, has a nominal flow rate of 22.5 gallons a minute. It will flow up to 30 with certain water conditions, and then into the CDIT and VNX module. So the VNX module here has we have a max module, and that flows at 66 gallons a minute and up to 100 gallons a minute, again, depending upon the water quality. Another view, this is a pictorial view of the various products. So here's your LabXT in the upper right. Our MX module looks like this. And then the LX used in the power industry, and the VNX. And then very importantly, here's our power supply, the DC3. So this is very important as OEMs are building systems. It makes the whole process simple, and it's designed for these modules. A little bit about the LX series. So this is a medium flow product for the power market. It was introduced in 2001. We offer 6 models from 2 to 22.5 gallons per minute nominal flow. This is a thick cell design in which both the dilute and the concentrate spacers are filled with resin. It's designed for high pressures up to 100 psi, continuous operations up to 113 degrees Fahrenheit. It's ideal for systems, say, up to about 100 gallons a minute. Has 4 simple plumbing connections, as you can see here. And it has high water recovery up to 95%. And then the VNX series. This is what we recommend for high flow applications. This module was introduced in 2004. We offer 9 models from 15 to 66 gallons a minute at nominal flow. This is ideal for high flow systems and ideal for power plants. It's designed again for high pressures, 100 psi up to 113 Fahrenheit, continuous operation. Again, 4 simple plumbing connections. You can see them here in this picture on the end. And it's designed for high recovery up to 99%. It's utilizing a fiberglass FRP housing with our patented flex mount end blocks. So that's these here. These are designed so that you can stack these modules on top of each other. It's also easy to move them around. You can move them around with a simple sling. So very easy to build a system and to move these modules around. The VNX series offers a wide range of module types. So on the top here, you'll notice we have the VNX Max, the Mini, the EP, and this is a smaller version of the EP. These modules here are ideal for the power industry, and most typically we use these in those systems. The Max, again, flowing up to 66 gallons a minute at nominal. The Mini is a great option because it's not as long, so it's shorter in length at 52.8 gallons per minute. The VNX EP 55 is a 55 gallon a minute nominal product. It's the same length as our VNX Max. And then we offer a shorter VNX 28 EP, which is shorter yet at 27.5 gallons a minute. We also offer several modules that are optimized for the microelectronics industry and producing over 18 meg water, the VNX E and the EX. In addition, then we have the VNX 55HH and the CDIT. These 2 modules were designed for higher feed flow challenges and product water up to over 16 megohms. Some of the advantages of the VNX over our LX is that basically you've got a larger module that's larger building blocks, and it occupies less space. So that's a big benefit when you're building a system. You've got reduced piping cost, reduced frame cost, it's easier to assemble, fewer connections, fewer power supplies needed. So, you know, there's a lot of reasons to use the VNX in these high flow applications. It generally offers a smaller footprint for end users, a huge benefit in the plants. Some of the first CEDI systems used an LX30 module at 15 gallons a minute each nominal. Here you can see how we have evolved from a skid with 45 LX30 modules with an overall flow rate of 675 gallons a minute to a skid using 10 VNXs, VNX Maxes in a much smaller footprint. So, you know, obviously a big advantage there. The VNX has 4 simple plumbing connections or piping connections. You've got dilute in, dilute out, concentrate in, and concentrate out. Some of our competitors require additional separate electrode streams, which do not have, we do not have on our design. So that makes our skids simpler and you know, easier to build. This slide demonstrates the flexibility of the VNX connections. You can have the product or the reject inlet and the outlet on the same side of a module, or you can also have it on the opposite side. So a lot of flexibility there. The electrical panels, electrical connections are equally as simple. You've got one pre-wired junction box with one conduit connection per module. There's a red wire for the DC positive, a black for the DC negative, and a ground wire. We generally recommend that any CEDI system is fed by a single or a double pass RO. So shown here are the maximum conditions for the feed water to the CEDI. The CEDI feed water must be carefully controlled to prevent membrane and resin fouling. This slide shows the typical VNX water quality when using 2-pass RO. The VNX is capable of greater than 17 meg water with over 95% silica and boron removal at nominal pressure drop and around 30 PSI. Very importantly, IonPure has designed several state-of-the-art power supplies. We offer a DCR rectifier on the left, which requires a separate isolation transformer, or you can use our DC3, which is on the right. And this is a 3-phase switch mode power supply with a built-in isolation transformer. We've also recently improved the efficiency of several of our VNX modules where under certain circumstances, you can actually run 2 modules from one DC3 power supply, further reducing cost. If you go to ionpure.com, you can get the specs on the DC3 and all of our products, but this is just to demonstrate that. You're free to go on and log in and register and pull this information right off the web. We also offer a touch panel display that has firmware that's fully completed and fully functional with the DCR-M version and the DC3 power supply right out of the box. This unit can operate up to 16 DCRs or DC3 power controllers, and it uses Modbus communications on the DC3. I'd like to compare some of the attributes of mixed bed DI to CEDI here. As I mentioned, mixed bed DI is a batch process, and as such, it requires constant labor and chemicals for regeneration. CEDI, on the other hand, is a constant production process requiring minimal labor such as daily parameter logging. The main costs for mixed bed DI are chemicals, labor, and resin, and the main costs for CEDI are the module replacement themselves and electricity. So there's a significant difference between these two technologies. Looking at this slide, you'll see a cost comparison of a typical 1,000-gallon a minute mixed bed DI system versus a CEDI system. You can see the high cost of the chemicals and the labor associated with mixed bed and compare that to the module cost and the electricity costs for CEDI. The CEDI system represents a 54% savings over mixed bed, or about $88,000 annually in this example. And this is based on a conservative estimate of the module life, when in reality, if properly maintained, our modules can last for years longer. We've got some modules that have been in use for over 10 years. Another factor to consider are the intangible costs associated with the handling of the hazardous waste chemicals with a mixed bed system. You really need to consider all the costs when evaluating these two technologies. Examples are employee safety and training, containment equipment, regeneration, chemical storage, and other costs. Here, demonstrating that there's a floor space savings associated with CEDI versus mixed bed. You can see it's possible to save over 50% on the floor space, and that space can then be redeployed to other uses. So that's a huge advantage as well. I'd like to share with you our standard warranty, autopsy services, and some other resources that are available. So we provide a standard 3-year prorated warranty for all our industrial CEDI modules, provided that the units are installed and operated to our specs. The feed water must meet our minimum requirements. And we also offer module testing and autopsy service from our factory in Tewksbury, Mass. If there was a problem with the module and you'd like to find out, why that happened, we'll receive in your module and do a complete analysis of every critical aspect on the module to determine what might have gone wrong and provide a written report, including photomicrographs of the resin, as well as chemical analysis of any contaminants that we find as needed. Some of the other resources available at ionpure.com. We encourage you to become a registered user and gain access to many of these resources, including the IP Pro projection software, technical material, drawing software updates, regulatory certifications, and many other pieces of information that will be helpful. You can also sign up for our newsletter and get the latest news on product notifications handled by our product manager, Pat Buzzle. And here's an example of an IP Pro projection. This online software program is very easy to use. You add the RO water chemistry to the program along with your required flow rates, temperature, and module type. The program then provides a projection report giving you the output flows, the water quality, recovery, pressure drop, the power use, voltage, current, and many other details. So a great tool, real good resource when you're designing your system. I wanted to show you a few examples of installations. So here's one in Pueblo, Colorado. So this would be on the smaller size. And to give you a little bit of history, the site originally used pretreatment of cation and anion and then into mixed bed deionization. They upgraded to RO mixed bed and then further upgraded to CEDI to reduce waste and operating costs using the VNX module. And this is a view from the inside of the plant, and you can see that they spent some $60,000 per year on chemicals with 2 regenerations per week. This cost was reduced and the water system was actually expanded without increasing the footprint. So a real success story. And a flip side of that is here's a very large installation in New York City. I'll show you some details here. This is one of the largest district heating systems in the world, using 6,760 gallons per minute of demineralized water with RO CEDI. This is serving 2 dual fuel combustion turbines and 2 heat recovery steam generators. But this system has 10 skids of 45 LX30 modules in operation, and they produce half of the steam for Manhattan. If this were built today, you'd be using VNX modules in a much smaller footprint, but this is a system that is still running today. It's been running successfully for many years. This is an isometric view. This is a huge plant, multi-story equipment on many different levels here. And here's another example of a system using IonPure CEDI modules. You'll notice this is a small footprint for this skid, a very simple manifold here, and the electrical panel. Very well-built skid, ideal example. And I want to thank you for your attention today, and I really appreciate that. If you need to contact me, my contact information will be available and sent out. And we're going to now start the question and answer period.
Thank you, Mike, for that insightful presentation of our technology and its advantages. I want to let all of our attendees know that you can access our power brochure directly from this presentation under the handout section of your control panel. We will also follow up with copies of our presentation today after our webinar conclusion. This takes us to our Q&A section, like Mike mentioned. I'm going to be throwing the very first question to Mr. John Wood. You didn't mention anything about hydrogen gas. Do IonPure CEDI modules generate hydrogen, and are there any special precautions necessary in order to deal with the gas generated by the CEDI modules?
Thank you, Sonia. All EDI modules actually generate hydrogen gas in, amount that is proportional to the amount of DC current that is applied to the modules. So IonPure modules aren't any different than other EDI modules in that respect. As far as precautions with the hydrogen gas, normally what people do is just send the reject stream or the stream that contains the gas to an atmospherically vented drain, and then the hydrogen, which is very light, just escapes into the atmosphere. And the amount of room air turnover that's required by normal building codes is then sufficient to cause the hydrogen to dissipate and to mitigate any potential safety risk.
Thank you for that, John. The next question is, are there any concern about discarding the reject water from the CDI system? Mike, you want to address this one?
Yeah, so generally the water is cleaner, the reject water is cleaner than anything you'd put down the drain, so there's no issues associated with that, no.
Okay. I'll send the next question to John. Again, boiler feed water often has a specification of 100 ppb TOC. What effect will CDI have on TOC?
Okay, TOC is primarily, CEDI is primarily a process to remove ionized or ionizable materials. So a lot of TOC is not ionized and therefore would not be removed. So in general, we would say that in order to remove TOC, both has to be ionizable, but it also has to be small enough to be able to diffuse through the ion exchange membranes. And you know, it's difficult to predict whether or not we could remove TOC because TOC is a non-specific analysis. It doesn't really tell you what the material is. It just tells you that there's carbon in it. So we don't make any claims about a TOC removal. In general, in order to meet that 100 ppb TOC specification, you would have to ensure that the water feeding the EDI system met that 100 ppb. And then the EDI would not contribute additional TOC to that water.
Okay, perfect. Thank you for that answer. Mike, next question I'm going to send to you. Can you do CIP, clean in place, on a CDI system the way you do in an RO system to remove foulants or scale? Can you reuse the same cleaners?
You can do a CIP. I would like to defer that to John to talk about the specifics because he's got some great experience with that. John, could you further add to that?
Yeah, actually, we can use more aggressive cleaners than you can use on RO membranes because the EDI modules for cleaning can tolerate pHs over 13 and less than 1. But the other part of that question was whether you could use the same cleaners that you would use for an RO membrane. And unfortunately, that's not always the case. The RO membranes are different than the ion exchange membranes in an EDI module. And so we have found that certain RO cleaners are incompatible with the membranes and resins in our EDI modules. So you can't necessarily use the same cleaners, but we have kind of a wide range of effective cleaners that are available for use on EDI modules.
Here's the next question. Why is there a reject feed into the modules?
Do you want to take that? You need so EDI is a concentration process where, as Mike mentioned in the presentation, you transfer salts from the mainstream, which is 95% of the water going through the module. That's what we call diluting or product stream. You transfer salts out of that stream into a smaller stream, which is the reject stream, which constitutes only 5% of the water going through the module typically. So the modules are constructed that those streams remain separate, and they're separated by the ion exchange membranes. And you want to be able to control the pressures in both various compartments, the diluting compartments and the concentrating or reject compartments. So in order to do that, you have separate streams with separate hydraulic controls to both monitor and control flow and pressure through the various parts of the module.
Thank you, John. The next question addresses CO2. The CDI feed water specifications table did not specifically mention CO2. Is there a maximum for CO2, and will CO2 damage the CDI module?
Okay, I'll take that, Mike. CO2 will not damage the EDI module, but it represents a portion of the ionic load on the module. And the main issue with CO2 is that it's not very conductive. So if you just do a conductivity measurement, often you're not detecting a large amount of the ionic load on the EDI module. So the issue with CO2 is that you don't know how much is there unless you do a specific test for it, which is done with a simple field test kit. We have this measurement called the feed water conductivity equivalent, and Mike showed that in that feed water table. That actually incorporates CO2 as part of that total ionic load. But just to give you an idea, he gave a maximum of about 40 microsiemens per centimeter FCE, or feed conductivity equivalent. If that were all carbon dioxide, it would be roughly 14 parts per million of CO2.
Perfect, John. Thank you very much. Our next question is, what is the general maintenance requirement of CDI units? How does this compare with MBIX?
Mike, do you want to take that, or you want me to?
I'm going to let you go with that one because I think your perspective there.
Okay. With a regenerable deionizer that you're regenerating on site at your plant, first of all, you generally need an operator present to kind of monitor the regeneration process, which consists of backwashing the resin to separate it into the anion resin and cation resin layers, so that you can put the acid through the cation resin and the caustic through the anion resin. And then after those chemical regenerants have gone through, then you need to rinse out the residual chemical, and then you need to backwash the resin if it's a mixed bed to put it back into the form where it's ready for use. So you monitor that whole process, but then in addition to that, you need to do maintenance on the equipment that makes that process possible. So that's the chemical feed pumps for both the acid and caustic, and all of the valves required to perform backwashing and mixing and rinsing and fast rinsing and dilution of the chemicals and all of that. So there, chemical metering pumps require constant maintenance. So there's a lot of maintenance on an ion exchange system. On the CEDI system, basically you've got a system that is flowing water through it, and whenever the water is going through it, then you have a DC power supply providing energy to remove those salts. So the main maintenance is just going once a day to take a look at the system and writing down some of the operating parameters like flow rate and volts and amps applied, and pressures on the inlet and outlet and that sort of thing. In some cases, that might be information that can be obtained electronically if you have, for instance, pressure transducers instead of pressure gauges and that sort of thing. So that would decrease the amount of monitoring required of the operator. So there's not an awful lot of maintenance. You don't have chemical pumps that you have to rebuild on occasion. You just have to kind of keep an eye on the system and make sure it's getting the power from the power supply when it needs to.
Good. Next question is IonPure, does the IonPure unit come with a rectifier, or the rectifier is not part of the Evoqua equipment provided?
So I'll take that. The rectifier is not part of the equipment provided. So we offer the various modules and the power supplies, and so it's an option if you want to buy the power supply or the rectifier. You don't have to. You could actually use your own. We highly recommend that you use one of ours because these are designed and optimized for the modules, but it's not required.
Thank you, Mike. How long after a CIP does it take to rinse to quality before production of product water?
I'll take that one. So the initial rinse after the CIP is typically just 10 minutes or so to flush out most of the chemicals before you turn on the DC power supply. Once you turn on the DC power supply, with our current modules, then you'd probably be looking at somewhere about an hour or so to get to a product water quality of about 0.1 microsiemen or 10 megohm, 1 to 2 hours.
Next question is, there's a problem if I install the UV TOC up from the CDI, as some hydroxyl radicals might be present after UV TOC?
I'll take that. We have not seen that be an issue. I know a lot of people have expressed that concern about hydroxy-free radicals coming off of UV systems. Hydroxy-free radicals are very short-lived, so I think it would be very unlikely, even though they are generated in the UV, they are generated at relatively small amounts, and I think that after a few feet of piping downstream of the UV, they would no longer be present.
The next question, do you have any figures for initial investment comparison between RO followed by IonPure and MixBed?
I'll let Mike take that one.
Yeah, we've done studies on this, and the studies, are really based on the plant conditions and how the system is designed. So there are so many variables. For example, the cost of electricity in one region can be different, than another region. The water chemistry is different. So all these factors can enter into that. And so it's very hard to generalize, but we don't produce or publish any standard figures for that, for those reasons.
As a follow-up, I would say that we will reach out to you separately if you have any existing operation that we can work with you in regards to analyzing that data for you and working with you on it.
Yeah.
That takes us to the conclusion of our presentation today and the end of our questions section. We want to thank all of you for joining us here today to learn about our IonPure leading technology. If you have any additional questions or for quotation requests, please reach out to our team. Our information is available here as well as on our website, and we will be sure to follow up with you with any other questions that you have for us separately. Again, thank you for joining us, and we look forward to speaking to each and every one of you. Have a great day.
Thank you.
Bye.